Hello, good evening, and welcome to Fundamentals of MIMO Wireless Communication tutorial. I am Rubina Afrin, Prime Minister Research Fellow from IIT Hyderabad. So today we will be discussing some concepts from week 5 lectures, and then we will be moving on to solve some assignment problems. So this lecture will be recorded and put on YouTube, so in case you haven't attended, you can join and watch anytime as per your convenience. So now we are moving on to wireless communication. So, uh, firstly, we will see what are the assumption of a classical IID channel. So, in any communication system now, from now onwards, we are assuming some assumptions about this classical IID channel. So, I'll just write it down for you. So, the first assumption is that delay spread is negligible. And the second assumption is that we can model H, the channel matrix, as zero mean, circularly symmetric, complex Gaussian with unit variance. So we will see what each of these terms mean. Okay, so firstly we will see zero mean. We know that H is a complex channel. H is a matrix, channel matrix. So each term of Hij, each Hij term has zero mean. So this is how zero mean came from. Zero means that scattering is uniform in all directions, right? Like we have seen previously that isotropic antennas are there. So scattering is from all directions. If scattering is from a single direction, more power is there, then we can model it as Rician channel or something like that. So zero mean means that scattering is uniform. That is why the mean is zero. Okay. Next we will see circularly symmetric. So what does circular symmetry mean? So circular symmetry is uh, given by a property that expectation of e to the power j5 of e to the power j5 into z equal to e to the power j5 into expectation of z. If this property is satisfied, then the random variable z is said to be circularly symmetric. So the channel is circularly symmetric, zero mean, and complex Gaussian. You know that the channel is h equal to hi plus j times of hq, where both hi and hq are uh, Gaussian, zero mean Gaussian random variables. So uh, from here we have seen zero mean, circularly symmetric, and complex Gaussian. Complex Gaussian because both the in phase and the quadrature, both terms are Gaussian. Okay. Uh, then moving on to especially white channel. So especially white means that the rays are coming from all directions with equal probability. Okay, so there are some properties of especially white channel. So I'll just write it down once. first thing is that each term of the especially wide channel is zero mean. Like we have seen here that uh, h is zero mean. Each term of h is zero mean. So especially in especially wide channel, each term expectation is zero, and then variance of each term is zero. Variance is one. So we will write it like this is equal to 1. And then correlation between uh, two terms of H matrix is 0. That means that the adjacent channels are uncorrelated. So I'll write it down as HWij into HWMN conjugate. This is equal to 0 if y is not equal to m and j is not equal to m. Then previously we have seen that the correlation diagram you must have seen. So we have seen that the correlation is 0, and we have found out that if delta x, that is the antenna separation, if delta x equal to 0.38 times lambda, or we can uh, approximate it to lambda by 2, in such a case correlation is 0. Okay, so what happens is that if antennas are separated at a distance more than this, more than 0.5 times of lambda, then there is no correlation, right? There is no correlation between the two signals that are received, that are perfectly uncorrelated. But if the antennas are separated with distance that is less than this d, then what happens? Then there will be correlation, right? So if correlation is there, then the channel matrix will be modified. So here, especially wide channel, what we have seen is that the channels are uncorrelated. This is uncorrelated. The correlation is 0, right? But if there is correlation, if correlation is there, then the channel matrix is modeled as, so now we will write wake of h is r to the power half times of wake of hw. Here our hw is especially wide channel, right? So what we have is that the correlation matrix into the wide channel will give us the correlated channel, right? Now some important things that we will see is that we will see the properties of vec first. uh, of, Before that, r is given by expectation of vec h into vec h Hermitian. Okay, so now especially wide channel, that hw we have is mr by mt, right? Because if there are mt transmitters and mr receivers, then we have the channel matrix as mr cross mt size. Okay, so now wake of hw will be mr mt times 1, right? We have saw this in previous week's tutorial also. We have solved some questions on this concept. So Vec, what this vec does is that it just stacks all the uh, columns on each other. Like suppose we have, I'll just take some space here. Suppose we have any matrix, I'll just consider a general matrix. 1 2 3 4 5 6 7 8 9. Suppose this is there. So we will just stack all the columns one above, one below the other. Like this is the first column, after that second column will be stacked like this, then third column will be stacked below the second, like that. So the 3 cross 3 matrix is now converted into 9 cross 1 vector. So likewise, vec of matrix HW will be MRMT cross 1. So this is HW, right, channel. So now what will be the correlation matrix size? Size of R would be MRMT cross MRMT. Okay. So from the knowledge of white channel and the knowledge of correlation coefficients, we can calculate the accurate channel, right? The channel with the correlation. Now some properties of R we will see. R emission will be same as R, right? So R is a positive semi-definite matrix. And we have seen that what happens in positive semi-definite matrix is that all eigenvalues are non-negative. Okay, now we have vec of h equal to r to the power half into vec of hw. Now suppose R is identity matrix. What does this mean? This means that H will be equivalent to HW. So that means that the cross correlation is 0, right? What does this mean is that our channel is especially wide. Okay. Now usually when there is some transmitter and there is some receiver, so the transmitter correlation is different and receiver correlation is different, right? So both of the values, if both of the values are given by R is the receiver correlation and RT is the transmit side correlation. Okay, so now we have this covariance matrix as RR, that is the receiver covariance matrix, and the transmitter covariance matrix is RT. So now the correlated channel can be written as RR to the power of half, then HW into RT to the power of half. This when you will use when covariance matrix is given at transmitter and receiver size. When transmitter and receiver covariance matrix is given. Okay, so in this case, the overall covariance matrix would be R equal to RT transports Kronecker product with RR. Now we will see what Kronecker product is. I'll just explain briefly. So here, as you see, uh, this RR has the size of MR cross MR because it is the receiver side covariance. RT has the size of MT by MT, and HW is MR by MT. Okay. So size of R is MRMT times MRMT. Okay, now we will see some properties of Kronecker product as well. But I guess we can take a question first. So you see this question. Here a 2 by 3 MIMO system model is given. 2 by 3 MIMO means 2 transmitters and 3 receivers, right? Then on the basis of this information, what would be the size of channel matrix? HW, especially wide channel matrix. It should be MR by MT. The 2 by 3 MIMO means 2 receiver and 3 transmitters. Okay, I'll see it again, but the size of HW is given as 2 by 3. So here you can see that receive covariance matrix at transmitter to the power of half is given, and then RR to the power of half is also given. So from here you can easily find the especially correlated channel matrix, right? The formula is RR to the power of 5 into HW into RT to the power of 5 to the power of half. So RR to the power of 1 by 2 uh, is given here, and then RT to the power of 1 by 2 is also given, HW is given. So you just put all the values and then you can find the especially correlated channel matrix. The answer will come as D. Okay. So questions based upon these are very simple. You just need to know the formulas. So first receiver covariance to the power of 1 by 2 into wide especially wide channel into transmitter covariance to the power of 1 by 2. Okay. So here we have discussed about Kronecker product. So very briefly I will just explain what Kronecker product is. So suppose A and B are any two matrices. Okay. So we have a matrix A of size, suppose n cross B, and a matrix B of size m cross Q. Then Kronecker product of A and B will be given as first term times matrix B, then second term times matrix B. Likewise, here it would be 1P into B. Likewise, here it will be starting with A n1, again matrix B, and likewise A n P into matrix B. So each term is multiplied by this M cross Q matrix, right? So uh, row in row, all the rows will be M times, right? Because in the place of every term of A, now M terms are coming. So the rows will be multiplied M times, and it is obvious that the columns will be multiplied then Q times. So the size of this Kronecker product would be Mn cross Qp. Okay. So this was one concept that I wanted to discuss. Afterwards, we will move on to again especially wide channel. So some basic things that you need to remember, because these questions can be asked direct straightforward in the exams. So I'll just write. So the first thing is that it is full rank matrix. Second thing is that it will contain MR-empty elements, because the size is MR cross empty, right? And then each element is zero mean circularly symmetric complex Gaussian. So now zero mean complex Gaussian, you all know. Circularly symmetric, you just need to know that expectation of e to the power j phi into that variable, random variable, is e to the power j phi into expectation of that variable. Okay. Now if there is correlation, then uh, the correlated matrix is now um, our receiver covariance matrix into wide channel into transmitter covariance matrix, right? So now the rank of HW is constrained by the rank of RR and RT, right? So see, HW is full rank matrix, but correlated channel we have as RR to the power of half HW into RT to the power of half, right? So from here, this is full rank, but now this rank of H depends upon the rank of RR and RT, right? So always rank of H would be less than equal to rank of HW. Okay. So this is one thing. Now we will move on to the statistical properties of our channel matrix H. So now onwards, when we are discussing channel matrix, we are not essentially considering it to be especially wide. Okay, if correlation is there, then we will just consider a normal regular channel matrix. Okay. So now, suppose we have empty transmitter and MR receivers. I'll just draw the diagram for once. These are the empty transmitters. And these are the MR receivers. And this is the channel. Likewise. So our channel matrix H is MI cross empty. First thing is that this H can be decomposed as UDV Hermitian, that is singular value decomposition. Okay. Now we all know that this U matrix and V matrix are unitary matrix. Okay. So U times U Hermitian is equal to V Hermitian times V, which is equal to IR, where R is rank of H and D is diagonal of sigma 1, sigma 2 up till sigma R, where each sigma is greater than equal to 0 and it is arranged in a decreasing order, like each sigma I is greater than equal to sigma I plus 1. Okay. So main thing that I wanted to discuss here is Now we know the channel matrix H. So H times H Hermitian would be, this is MR by MT. So H Hermitian would be MT by MR. So this would be an MR cross MR matrix. Okay. So when we decompose HH Hermitian, this can be decomposed as Q lambda Q Hermitian, where lambda is the diagonal, lambda 1, lambda 2 up till lambda MR. Okay. So these are the eigenvalues of H Hermitians. So this eigenvalues of H Hermitian are related to the singular values of H matrix. Okay. So now we will see that each lambda I is equal to sigma I square. That means each eigenvalue is equal to sigma I square. Okay, and this is true only if I is from 1 to R. After that it is 0. Okay. So essentially the ith eigenvalue of H Hermitian is equal to ith singular value of H. Right, square of ith singular value of H. So this is one thing. Now we see that H we have assumed as random, right? So now when it is decomposed into Q lambda Q Hermitian, so whenever H is different, every other realization of H will give every other realization of lambda, right? So what does this mean is that all the lambda, all the eigenvalues are random as well. Okay. So here one concept is that if H is HW, that is if it is especially white, then elements of HW into HW Hermitian are Richard distributed. You can go through, I think, lecture 20 or 20, 21 or 22 for more details on it. So basically, why I am discussing all this is, see, eigenvalues of HW and HW Hermitian. So this eigenvalue is like this contains the strength of the channel, right? So each lambda contains strength information of the channel. Okay, so the lambda term, since each term of HW is Rayleigh distributed, so each term of HW Hermitian, I mean the diagonal terms, that would be exponentially distributed, right? So we have lambda m is exponentially distributed, and since this is exponentially distributed, sigma m we will have as Rayleigh distributed. Now moving on to square Frobenius norm. So square Frobenius norm is given by HF square, and this is equal to HF square we can write as trace of H times H Hermitian, which is equal to sum of all the terms. So I equal to 1 to mr, j equal to 1 to mt with hij whole square. So this square Frobenius norm, this gives the total channel gain, total power gain of channel. Okay, and also H Frobenius square, this is given as I equal to 1 to mr into I equal to 1 to mr summation lambda I. Okay, and currently just now we have discussed that this lambda I is random. So this term square Frobenius norm of the channel matrix, this is also random. So now if this quantity is random, then it will have a probability distribution function, right? So the probability distribution function is given as, and this we will take when this is especially wide channel. Okay, so this probability distribution function is given as x to the power of mtmr minus 1 upon mtmr minus 1 factorial e to the power minus x into ux. This ux will ensure that it is greater than equal to 0. So now we can see that uh, this H Frobenius square is the sum of each Hij whole square. Okay, so each Hij whole square is a chi-square distributed function, right, with 2 degrees of freedom. And now the total term is mt times of mr. So hf square is chi-square distributed, but it is with 2 mtmr degrees of freedom. So before without wasting any time, we will move on to the special correlation. And now we will see that all the concepts that we have discussed previously, these will come handy. So we have discussed spatial correlation. We have been discussing since we have discussed the receiver correlation in terms of frequency. So from there we found out that the receiver correlation in terms of distance is given by J0 of 2 pi delta x upon lambda, I think. So when delta x is approximately lambda by 2, then correlation is 0. So what does this essentially mean is that we can separate the transmitter and the receiver with a distance that is larger than lambda by 2, and then the signals that we will receive, that will be uncorrelated, right? Now this concept is used in multiple antennas channel. Like we will study that suppose we have a single channel at the transmitter, a single antenna at the transmitter, and single antenna at the receiver. Now what we are doing is that now we are wait a second, this is not transmitter, these are the distance between the two antennas only. Okay, sorry for the confusion. So what I am trying to say is that suppose we have a single transmitter and single receiver. This is one single transmitter. See the color. So this is one single transmitter and one single receiver. So transmission is happening, but what if this channel goes into fading, deep fade, suppose it is going. So what happens is that at that time the whole channel is like gone, outage. So the channel just cannot be used. So the transmission will hamper, right? That will get that will so the quality of service will be poor. Okay. So now what I'm saying is that suppose now we take two antennas at the receiver, and both the antennas are now separated by a distance which is greater than the delta x that we have written here. So this is separated by a distance d which is greater than the delta x. So now what will happen is that the same signal, this is xt, this same signal will be transmitted to both the receivers, right? And now since they are spatially separated at a distance which is greater than the uh, critical distance, suppose I will say critical distance, then the signal received at both the antennas, both the receiver antennas, this y1t and this y2t, these will be uncorrelated, right? So now suppose if any one channel is broken, then again communication is happening, right? So this is the basic concept towards why we moved from single input, single output communication to multiple antenna communication. Mostly, they will be mostly what happens is that multiple antennas at the transmitter uh, will will be difficult to deal with than multiple antennas at the receiver. So here mostly we will be concerned about the single input multiple output system for a while. After that we will move on to the MIMO systems. So the initially the assumptions that we took, the IID channel assumptions, so that will be valid, and then we will assume a flat fading and slow fading scenario. Always we will be assuming flat fading and slow fading scenario, right? So now I will show what is the benefit of using two antennas at the receiver. So suppose this is the output SNR. Okay. So this, suppose this is from the first receiver, Y1T, from Y1T it is coming. And then we have the other one from Y2T, right? So now instead of one, now we have output at two of the antennas. So now suppose this is the threshold. Now you see the uh, two receivers are uncorrelated, right? The two signals that are being received at the Y1T and Y2T, these two are uncorrelated. So this will be like very least probable that the two signal will go to deep fade at the same time, right? Like suppose here you see signal from the first channel is has power less than the threshold one, right? But from the at the signal strength at the second antenna is fine. Likewise here you see and this channel will be going into deep fade, but this will be like that. So since both are uncorrelated, there is very high probability that the that both will not go into deep fade at the same time, right? So this is the basic idea towards why we are using multiple antenna systems. Okay. Now that we have two different antennas, and now we have got multiple received signals. So now what will we do? We have to do some combining at the receiver to get the optimum received signal, right? So two categories of combining we will read here. So first one is the selection combining, and the second one is the maximal ratio combining. So now we will start with selection combining. These are numbers. Okay. Special correlation we already discussed. So now we will move on to selection combining. Now you see, we had two signals. So we had like the variation of signal power at the receiver. So we will start our discussion from here only. Here I have discussed. Here I have made the diagram. So selection combining this. You see, there is a single antenna at the transmitter, and there are multiple antennas at the receiver. This is the receiver. So after getting the signals, there will be some combiner. Okay. So in selection combining, the combiner is basically a switch. What is the function of this switch? I'll write it more neatly. This will select output with maximum power. So at every instant, it will select the output which is at maximum power. So I'll just show it with the diagram. So here we have taken three antennas. So we will go with three antennas. So this is the output SLR. This is the time axis. Now suppose the signal from the first antenna is varying like this. Okay. Then we have signal from the second antenna. So now suppose it is going like this. And we have the third antenna. So suppose third antenna is signal part from third antenna is going like this. Okay, so now what happens in selection combining is that it will select the output with maximum power, right? Here the switch is there, it will always select the output which has the maximum power instantly. At every instant it will be just checking, and whenever the whatever is the maximum power, it will select that one output. So now you can see, I'll just draw here. So at this time instant, this has the maximum power, right? After this has the maximum power. It will go till here like this. After this channel has the maximum power. Then this one. Then it will go till here. Then here. So likewise, at every instant, it will just see which among the three antennas is having maximum power. Right. So now, one advantage I'll tell you. Suppose this is the threshold. Now you see, once in some time every channel is going into deep fade, right? But when we are doing selection combining, the received SNR goes way up from the threshold. Okay, so now the outage probability will be very less. You can see from here now that outage probability is very less. In fact, if you take 3 antennas, then the outage probability is like uh, negligible. There will be no outage. So from here we can see that it is very beneficial. Some pros and cons we will discuss now. Okay. So now you see, from this diagram what and all is happening here. Okay. So first thing is that level crossing rate is changing. Right. What else is there? Average duration of fade is changing. Then dynamic range of fluctuation is changing, right? See, from the first antenna, the dynamic range of fluctuation was from here to here. From the second, it was here to here. Okay. The third one was fluctuating from here to here, right? But now the equivalent signal is fluctuating only this much, right? So the dynamic range of fluctuation is decreased. Okay, dynamic range is maximum to minimum the range. Okay, what does this mean is that the variability of signal is less, right? Because now it is not varying too much. Variability of the combined signal, because we are doing combining at the output, right? So variability of the combined signal is less. And the signal part, the signal average is also increasing, because essentially now it is like the power is now more. Okay, so some mathematical stuff now we will discuss. Now consider this diagram. Okay, now we have suppose MR receivers. So maybe I can copy the diagram. Okay, so now we have one total MR receivers. Okay, each receiver will have one channel, right? H1, H2 up till HMR. Okay, so how will we write the signal at the output? We can write as yi equal to hi times of x, because this symbol is 1 only. Na? So hi times x plus, since multiple receivers are there, so multiple noises will be there. Okay. In the previous class also I had described this, because noise arises at the receiver side, no, uh, because of the hardware defects or something like that. So yi equal to hix plus wi. Here I will range from 1 to 2 mr. Okay. So what we are saying is that the after selection combining, yi star is hi star times of clarity. I will write it as S. The symbol, the hi star times S plus wi star, where I is, I star is argmax of hi square. This means that I is the value, is that value for which the power of the channel is, that means the channel gain is highest. Okay, so what we are doing is that at every instant the highest power branch is taken, right? Okay, so this is the uh, received signal equation for each branch. Okay, so what will be the SNR at each branch? SNR will be gamma I mod of hi square into expectation of si square divided by expectation of wi square. So here we are assuming that every branch has the same power, and every noise element also has the same, like noise variance is also same, and then signal power is also same. So what we are essentially saying is that this is our assumption. Expectation of SI square is PS, and expectation of WI square is sigma W square. Okay, so what about this ratio? Expectation of S square by expectation of W square. This is PS by sigma W square. This you can say as SNR of each channel. Okay, so now this HI we have considered as a relief feeding channel, right? So PDF of SNR, so PDF of SNR is given by 1 upon gamma into e to the power minus gamma I upon gamma. So this gamma we can now write it as, we can assume that the uh, SNR at each branch is equal to the average SNR only. So that's how we can write it as. So now we know that the SNR at each branch we know. Okay. So now average SNR, this gamma bar, what is this? This is average SNR on ith branch. That means average SNR at each branch, if we say, that is the gamma bar. Okay. So how do we take average? We take average by doing expectation, right? So we can write that gamma bar is expectation of gamma I. Okay. Now gamma I we know. This is expectation of mod hi square into gamma, right? So that is how we are getting the average SNR. This since both of these, this is not a random variable, so this would be like expectation of mod of hi square into expectation of gamma. And these are two independent random variables because this gamma has a PDF also. So expectation of gamma we can write as gamma bar, and this is 1. So this is how we are obtaining the gamma bar. Okay. So now if all of these are explained in the class also, outage probability if we write. So outage probability is given by probability that gamma A is less than equal to gamma PH. This is the outage probability for any channel. Okay. So this is not the overall for selection combining, but outage probability for any link. If any link is in outage, what is the probability that it is in outage? So this outage probability, if you will calculate, so you will get it from integration 0 to gamma threshold, and then P of gamma I into d gamma I. Now you know the PDF probability distribution function of SNR, this gamma I. So P gamma I you already know. So from here, if you integrate, this is when you integrate this with respect to d gamma I, so we will be getting an output of 1 minus e to the power minus gamma threshold by gamma bar. Okay, so this is the outage probability. But this outage probability is that probability that the signal is falling below threshold for any of the link, any one of the link, right? So this P naught is that probability that signal falls below threshold for any link. Okay. So now again you consider the selection combining scenario. I'll just explain with the diagram only. So we have one transmitter but multiple receivers, right? So even if any of the channel is in fade, the other one, if it is working, then it will not be outage. Okay. So for outage, all of the links, all of the signal, like for all the links, the signal value should fall below the threshold, right? So for selection combining, we can say that outage, when will outage happens? Outage happens when all M branches are in fade. Is less than all branches SNR, better to write gamma M is less than gamma theoretical, right? So what does this mean is probability that gamma 1 and gamma 2 and gamma 3 and so on up to gamma MR, all of these are less than gamma threshold. Okay, so probability that one of the link is in outage is given by this. So probability that all the M links are in outage, this will be given by 1 minus e to the power minus of gamma threshold by gamma to the power of M, right? So this is the outage probability for selection combining. Okay. Now if we say coverage probability, so coverage will happen when if any of the link is working, right? So coverage probability will be 1 minus outage probability, that is 1 minus e to the power minus gamma threshold by gamma bar to the power of M. Okay. Right. So other than that, so PDF of gamma we can write as d by d gamma of I'll just show you. PDF of gamma will be d by d gamma of probability that gamma is greater than gamma, right? So when calculated, this will come as m times 1 minus e to the power minus gamma threshold by gamma bar to the power of m minus 1 into 1 upon gamma bar. You are differentiating this term. So e to the power minus gamma upon gamma bar, right? So if this is the PDF of gamma, then what will be the mean? Like post processing mean, we call it post processing mean. Post processing SNR, if we want to find out. So this SNR would be 0 to infinity gamma t gamma d gamma. When you integrate it, so the integration is basically complex, which involves some numerical methods and all. So I'll just write the formula, which will be beneficial for solving the exam papers and the assignment questions. So this much, I think this much is sufficient for you. So this is gamma bar times of summation I equal to 1 to mr 1 upon I. So this we call as post processing SNR or post combining SNR. SNR post combining for selection combining, right? So from here we can see that the uh, average gain is increasing, right? But it is increasing with term 1 upon I. So suppose we are adding second antenna with first antenna, then there will be lot of difference. Then after the difference will keep getting less. Okay. So this is increasing with them, but it is not increasing linearly, right? So what is happening is that as we are increasing the number of antenna, so the variability will be less, right? The signal fluctuation will be less only. uh, I'll show this diagram again. The signal fluctuation will be less, the variability will be less. Okay. So outage, like when you increase from one antenna to two antenna or to three antenna, then outage will decrease. But when you keep increasing the number of antennas, then outage probability will not have much of effect. So this I'll show in the diagram. This diagram I've taken from Andrea Goldsmith. So now you see the outage probability is on this axis. So when m equal to 1, this is the outage probability diagram. M equal to 2, there is a huge shift, right? At the same SNR, like normalized SNR, there is a huge shift. After that, m equal to 3, there is a little, m equal to 4 is a little. So as we keep increasing in, the effect will keep decreasing, right? So that's what. And so that's what I wanted to discuss about selection combining. So what is happening is that outage probability we are taking now. That outage probability is the product of outage probability of each link. So suppose like the first link has outage probability of 0.1. Second one, so suppose identical outage probability is there. So when receive antennas are 2, then what will be the payout? It will be 0.1 to the power of 2, right? 0.01. If 3 antennas are there, then outage will be 0.1 to the power of 3. like that. So the outage will decrease and the coverage probability will increase, right? So as I told that if three branches are there, then there will be hardly any outage. Okay. So now coming on to disadvantage. So what happens is that when selection combining is there, then uh, at every instant you have to measure power, right? So this is very cumbersome. Like this will be computationally very complex to measure the received power at every instant and then make decisions. This will be this will be involving lot of circuitry. So there is one technique called switched beam combining. Okay, here what is happening is that this switches only when SNR goes below threshold. Okay, so basically this will reduce complexity. Okay, I don't have the diagram anymore, so I'll draw a fresh one. So this is your threshold power. This is the output from the first link. This one is the output from second link. Okay, so what switch beam will do is that when the signal is going below threshold, then only it will make a decision, then only it will switch. So suppose here it is going from blue. Now here it will not switch, it will go with this. But here it is going below threshold, immediately it will see if the other channel is giving more output, more output power. So immediately it will switch, then it will follow on this one. Now here it is saying both of them are there in fade, so it will not make any decision. But here it will again come with this one. Again here it will switch. Then here it will switch. Then again here it will switch. Then it will follow this one. Then here it will come till here because there is no option. Then it will switch. And like that. So this is switched beam combining. Now the other thing is maximal ratio combining. So what happens here is that there is one transmitter and then there are MR receivers. Okay, but at each receiver, what we are doing is that we are multiplying the received signal by some weight factor. So these alpha are weight factors. Okay. So this is the first channel, second channel, like this, HMR. Okay. So here this is Y, but at this is Y1, this is Y2, suppose this is YMR. So output at any ith antenna will be the similar as the previous one, right? HIX plus WI. Right? After we are getting this Y, we are processing it. We are multiplying with alpha. Right here, we are getting all the Y's. After that, we are multiplying them with their weight factors. So for MRC, what we're doing is that this y now, this one. So this y is summation from I equal to 1 to MR, alpha I into HIX plus WI. So all the received signal from the ith antenna, all of them we are taking and we are multiplying them with the respective weight factor, and then we are summing all of them. Okay, so here also I will range from 1 to up till MR. Now what is the value of alpha? What product we are multiplying it with? So alpha is HI Hermitian. Okay, or when we are using this for decoding and all, then we will use the normalized alpha, that is HI Hermitian divided by summation, okay, mod of HK square. So either normalized one or this one. So for error probability and all, this one works. So this one is fine, we can use it. But for decoder design, we will want less complexity. That is, we will want less magnitude to multiply with it. So then we will be using the down one. So this is used for error probability. This is used for decoding. Okay. So now MRC, what happens is, what we got till now is y I equal to 1 to m alpha I HIX plus WI. Now we write alpha I as HI Hermitian, HI conjugate. So it will narrow down to mod of HI square X plus HI conjugate WI. Right. So we can write it as X times of I equal to 1 to m mod of HI square plus summation I equal to 1 to m HI conjugate into WI. Okay. So what we have done in MRC is that we have uh, multiplied each signal with its channel gain, right? So what happens is that if the channel is weak, see here we are giving some weight to the information, right? So if the channel is weak, if this one is weak, then less weight will be given, right? To this channel, less weight will be given. But if the channel is strong, if the channel power is more, then more weight will be given, right? Okay, so basically the weak channel will have less weight, right? So now what happens is that the error probability will go down, correct? because because whatever the source of error is there in channel, we are taking very less weight of that channel. So strong channels, we are getting the signal from the strong channels. So this is how MRC will work. Now all the calculations are there which I am skipping. So post processing SNR, I'll just skip to post processing SNR for MRC. So here if you see, we have the signal term and we have the noise term. Okay, so signal power is like expectation of I'll just write it down. I'll write it here only. Here see, P signal will be expectation of this into this conjugate. So it will come down to expectation of x square times of this term to the whole square. Okay, and then P noise will be this expectation of W square, that is the sigma square only, into summation equal to 1 to n mod hi square. So when we will take SNR, so SNR for post processing, like after processing, now if we see SNR, so we will denote it as gamma m MRC. This will be equal to expectation of x square by expectation of W square into summation I equal to 1 to m mod of hi square. Okay, so if we break it down, because there is mod of hi square, so if we break it down, it will be like expectation of h square by w square into h1 square, then same term into h2 square, like that it will be broken. So that we can write as SNR of first link plus SNR of second link, and likewise up till SNR of MRth link. Okay, so post processing SNR for MRC is summation I equal to 1 to m and then gamma I. Again, this gamma MRC has this term hi, which is a random variable, and then this is also random variable. So this will also be a random variable which will have its own probability distribution function. So this gamma MRC is chi-square distributed again. But here we see that only MR terms are there, right? So since each HI is having 2 degree of each HI square is having 2 degrees of freedom, it is also a chi-square distributed only, but it has 2 degree of freedom, and then m terms are getting added, so it will be having 2m degrees of freedom. Okay, in selection combining mr into mt degree of freedom were there. Okay, so now suppose we have to find now average SNR, average post processing SNR. So average will be expectation of this SNR, right? Expectation of this gamma m. So this will be equal to summation of I equal to 1 to m expectation of gamma I, right? This expectation gamma A is gamma bar that we have seen previously also, right? So this would be equal to m gamma bar. Okay. So this is very important actually. Two things are there. If we have to just calculate, if you have to just calculate the post processing SNR, and SNR of all the other branches are given, then you can directly use this formula to calculate the post processing SNR, right? But if we have been given the average SNR of each branch, okay, please note down this, because this will be like, this is generally asked in the exams and all, that what is given to you. If average power is given, average power for each link is given, then you can easily calculate the average post processing SNR. So always mind, if you are asked the post processing SNR only or average post processing SNR. Okay, so this is there. After that, just one last concept is there. This is outage probability. So outage probability is probability that this SNR post processing SNR, this should be less than threshold value. So PDF is given in there in the text, and when you integrate it from 0 to gamma theoretical, it will come as 1 minus e to the power of minus gamma threshold by gamma bar summation k equal to 1 to m gamma naught by gamma bar gamma threshold only. This to the power of k minus 1 divided by k minus 1 factorial. Okay. So here we have seen in MRC that this SNR is increasing linearly in MRC, right? So this is like very huge gain, because if we are using MRC, so the output SNR, the post processing SNR will be very high. So this will be like, this can never go to outage. Like outage probability will be very less. There will be huge potential gain. Right. So this is the probability of error for MRC. After that, coverage probability in MRC. This we'll see. But what I wanted to show that, okay, this is the outage probability. We will be doing the coverage probability in PDF. So PDF of SNR, as I have told here, that PMRC is given there. This is PMRC. Is given as gamma to the power of m minus 1 e to the power minus gamma by gamma bar divided by gamma to the power minus m into m minus 1 ka factorial. So now I won't be going into any detail, but bit error probability, this is given by integration from 0 to infinity q of square root of 2 gamma p gamma d gamma, right? So this thing will come as 1 minus g by 2 to the power of m summation n equal to 0 to m minus 1 plus mcm into 1 plus g by 2 to the power of m. Okay, so this is the better probability, and then I think next week we can see the symbol error probability, and then the approximation of the symbol error by using Chernow bonds and all. So one thing I would like to mention is that symbol error probability for MRC, you can see this in lecture number 25, I think. This is proportional to gamma to the power of minus MR. So what does this mean is that as the number of branches is increasing, so probability of error is decreasing, right? This MR is called as diversity order. Okay, so we will solve some question based upon this. So this is called as diversity order. Okay. Now you see, since it is depending upon gamma to the power of minus MR, right? So if MR is 1, then it is like, say, suppose MR is 1, then the probability of error is approximately gamma to the power of minus 1. If MR is 2, then it is gamma to proportional to gamma to the power of minus 2. So it is decreasing with the number of antennas increase, the probability of error is decreasing very much. So you can see that this m equal to 1 is there, and then m equal to 2 for the same SNR, very huge probability of error dip is there, right? Like for this SNR, for m equal to 1, probability of error is here like near 0.05 or something. But for m equal to 2, it is going beyond 10 to the power minus 3. So MRC is very, very beneficial. Like it increases the SNR as well, but it decreases the probability of error very much. So theoretically, this much is fine. Now we will see some questions and then we will close this meeting. So here it is saying that a SIMO single input multiple output system is there where the receiver has 4 branches. So 4 branches means MR is 4. Okay. Now instantaneous SNR is given minus 10 dB, minus 3 dB, 12 dB, 5 dB. Okay. Find the instantaneous post SNR that can be achieved with selection combining. So what happens in selection combining is that only one channel is selected, right? So it will be selecting the channel that is having the maximum power. So 12 dB would be the answer, right? We'll go back once and just check. This is the average SNR post combining. But the post processing SNR will be calculated like this only because only one channel is selected, right? So out of minus 10 dB, 5 dB, minus 3 dB, and 12 dB, only 12 dB will be selected. So this would be the instantaneous post SNR. Okay, if average post SNR is asked, then we can use this gamma var times I equal to 1 to MR 1 upon I. Okay. So here the answer will be 12 dB. Now here in this question it is asked that we have a selection combining receiver again and we have 4 receive branches. Okay. So 4 receive branches means M is 4, right? Then threshold SNR is 18 dB. 18 dB. We will always convert this into linear scale, right? So this is 10 to the power 1.8. And then average SNR of the branches is 20 dB. So this is 10 to the power 2. Now outage probability is asked for selection combining. What we have discussed in selection combining is that each of the channels should be in outage, right? So outage probability for one link is e to the power 1 minus e to the power minus gamma threshold by gamma bar. And for 4 receive branches, it should be to the power of 4, right? So this should be the outage probability. If we calculate it, it will go as 1 minus e to the power minus 10 to the power 1.8 upon 10 to the power 2 to the power of 4. So this when you calculate it will come as 0.0479. So how much is the outage probability? 4.79. 4.79%. Okay, so answer here would be B, 4.79%. Now you see what is the average post SNR for selection combining of 4 receive branches if average SNR is on each branch is 10 dB. So here selection combining is there, but it is asking average post SNR, right? So average post SNR, what we have seen here is average post SNR is summation I equal to 1 to m 1 upon I. Okay, this is for selection combining, right? So each branch SNR is 10 dB. So we have, and also average SNR is mentioned. So gamma bar is 10 dB. That is 10 only, right? So this would be equal to 10 times of, now 4 branches are there. So this will be 1 by 1 plus 1 by 2 plus 1 upon 3 plus 1 upon 4, right? So this would be 20.83, but this is in linear scale, okay? So we have to convert it to logarithmic. So gamma bar is C in dB. This would be equal to 10 log to the base 10 of 20.83. Okay. So this will count as 13.18 dB. Okay. So the hack is that always you should focus upon what is asked, average SNR or instantaneous SNR. Okay. Now you see here. In this question, it is saying that in the above question, find the post-processing SNR if MRC combining is used. Now we know that average post-processing SNR for MRC is M times of average SNR of each branch, right? And post-processing instantaneous SNR, this is I equal to 1 to MR gamma I. Okay, so now this is a continuation to the first question only. So for the first branch, I think the SNR is 10 dB. Second branch is 10, 5 minus 3 and 12. So this is 10 dB, then 5 dB minus 3 dB, and then 12 dB. So you have to convert each of them into linear scale. So this is your gamma I, gamma 1, gamma 2, gamma 3, gamma 4. Okay. So here you have to find the post processing SNR. So here gamma MRC would be sum of each of the SNRs. Okay. So I'm not sure what the answer is, but maybe we can do calculation. So this 10 dB is 10 only. 5 dB is 10 to the power 0.5. That is 3.16. 3 dB is 10 to the power minus 0.3. That is 0.5. 12 dB is 10 to the power of 1.2. That is 15.84. So if we sum all of them, that is 15.84 plus 0.5 plus 3.16 plus 10. So this is 29.5. So now when we convert it into dB scale, log of 29.5. This is coming is around 14.69, but I'm not sure. So maybe there is some error in the calculation. So I'll just see and maybe I can post on the discussion forum. Or maybe if you find the answer, you can post on the discussion forum. That will be highly encouraged. Okay. So now moving on to the next question. Now you see we have a MIMO system with one transmit and M receive system, that is SIMO only, single input multiple output system that we have studied yet. So if Yi is the output of ith branch at the receiver and Hi be the channel coefficient for ith branch, then which of the following represent equalization? So what we have discussed previously is that Yi is Hi times X plus Wi, right? So these are the received signals, right? After that, we are multiplying it with some alpha and then we are adding them and then we are getting the y, right? And this alpha is Hi Hermitian. So we are getting Yi here only. So after getting Yi, we are multiplying them with Hi Hermitian, right? And then we are adding them all up. So this is 1 to m, right? So which of the options is matching? Option number C. So always you just proceed step by step that what is happening at each receiver. It is saying like at each branch of the receiver. So you have to see that this is given as Yi. So Yi and here the transmitter is there. So these are the channels. And after that, after this part, MRC processing happens. Okay. So here it is asking the diversity order. Just now we have studied, right? That if we have the MR number of receive antennas and one transmit antenna, from MRC we are getting a diversity of MR, right? We are getting the error probability as gamma to the power of minus MR. So this will give the diversity. Okay, so we will move on to the next question. We again have one MIMO system with one transmit antenna and two receive antennas. Okay, so MR is 2. It is saying that each branch receives an independent relay faded channel, the signal, and the average SNR is given here. Okay, so here you see average SNR is given and you have to find average output SNR. And what combination is used? MRC combination. So what is the average SNR for MRC? This is equal to M time of average SNR for each receiver, right? So now here average SNR for each receiver is given as 10 dB. So this is 10 in the linear scale also. So average SNR for MRC would be, since there are two receive antenna, M is 2, 20. So after that when you convert it into dB, this will be 10 log of 20. That is approximately 13.01, which you can approximate to 13 dB. So here answer would be 13 dB. Okay, always you have to see that you have to calculate average or instantaneous post processing SNR. So this is uh, one major thing of confusion here. So always you have to see, like if you have to see if you have to obtain the average output SNR, then you will use the formula for average one only. You don't have to get confused in it. Okay. And this question has been discussed so many times that the minimum spacing between two antennas to observe two independent fading channel. So this will always be given by delta x equal to lambda by 2. Okay, because we know that the correlation varies as j naught times of 2 pi delta x by lambda, and it goes to 0 when delta x is approximately 0.38 lambda, but we then round it to lambda by 2. Okay, so we'll move on to the next question. So this is like linear algebra question. Which statements are true for Hermitian matrix? So some properties of Hermitian matrix is, what is Hermitian matrix first of all? So for Hermitian matrix, A Hermitian is equal to A. Okay. So some properties are that all the eigenvalues are real. Okay. So first option goes off because eigenvalues cannot be complex. All the eigenvalues are real for the Hermitian matrices. Okay. Then eigenvectors are not column of Fourier matrix. Their eigenvectors are orthonormal, orthogonal to one another, but they are not from Fourier matrix. So the answer here would be B. Then this is Cauchy-Schwarz inequality. This is like theoretical only. So here inner product will always be less than equal to the length of U into length of V. So then we have the Kronecker product it is asking. So we have already discussed what is Kronecker product, like each term of A will be multiplied to the matrix B, right? So now we'll solve A Kronecker B and then B Kronecker A. You can try and then you can check. So for these matrices, A Kronecker B would be first term of A, that is 1, into B matrix 1 0 1 1. Okay. Then second term of A into 1 0 1 1. Then it is we come to the next row and then the last term into 1011. Now what matrix it is giving is, this is 1011 only, then again 1011, here also 1011, and this will be negated 10 minus 1 minus 1. So I guess only A and B are matching, right? Now we calculate B Kronecker with A. So this will be equal to first term of B and then 1 1 1 minus 1. Then again here it will be 0 0 0 0, right? And then again here it will be 1 times 1 1 1 minus 1, and then 1 times of 1 1 1 minus 1. So it will be 1 1 1 minus 1, and this one is not true because here 0 is there na. So the answer would be option A in this question. Okay. So this one is an interesting one. This is also pure linear algebra question. One matrix is given and then very basic question is their eigenvalues, trace and determinant satisfies which of the following. So some properties you should know that product of eigenvalues is determinant of A, right? Now we see the determinant of A would be 6 times 0, 4 times 0, 5 times 0. So determinant is 0. So here product of eigenvalue is coming as 0, which means that one eigenvalue must be 0, right? Okay. Now second thing is this first thing. The second thing is that sum of eigenvalues is equal to trace of A. Okay, now you see the options. One eigenvalue must be 0, A is shortlisted only. But then you see another things. Determinant is 0 and sum of eigenvalues is equal to trace of the matrix, right? So sum of eigenvalues is equal to trace of the matrix. So answer would be A. Now you see the MIMO channel matrix H is given here, and then we are getting asked the eigenvalue of HH Hermitian and square Frobenius norm of H. So a straightforward method is to just calculate HH Hermitian. It is asking HH Hermitian only. So HH Hermitian, if you calculate, it will be 0 0.3, 0 0.2, 0 0.1, 0 0.2. And then Hermitian of this one. So this will come as 0 0.13, 0 0.07, 0 0.07, 0 0.05. Okay. Now you see, the trace of this matrix would be the sum of eigenvalues, right? So trace of each time H Hermitian is sum of eigenvalues, right? And also from the previous discussion that we have done currently for Frobenius norm, this is only equal to Frobenius norm square of H. So now you see sum of eigenvalues is trace. So that is equal to 0.18. So the 0.18 is the Frobenius norm also, Frobenius norm square, and the sum of the eigenvalues. So 0.18 is the Frobenius norm square. This should be the answer, but then you should verify the sum of the eigenvalues. So this is also coming to be 0.18. So that is how you have to approach this kind of problems. Okay. Now this we will see. Before that we will discuss this question. So this is very easy question. This is given a matrix. This is a straightforward linear algebra question only. So you can see from this matrix that it is not symmetric, right? So this option is not there. For full rank or rank 2, what you will do is that you will calculate the determinant, right? So suppose this is matrix A. So now you calculate the determinant of A. This is like 4 times of some minus 14 minus 5 times of 16 minus 12 is like 4 plus 7 times of 56. So anyhow this is not going to be 0. So this matrix is not rank 2 matrix, it is just a full rank matrix. Okay. Now we will come to the last question. This thing is given in lecture 26, the theoretical part, the proof you can go and see in lecture number 26. So here, see, upper bound on probability of symbol error with MRC combining is given as PE is upper bound is n times of rho d min square divided by 4 times of MR to the power of minus MR. Now I'll explain what each of these terms mean. So N is the number of nearest neighbors. I'll just write it as nearest neighbors. And then d min is the minimum distance, right? So for 16 QM it is 0.6325 times of square root of ES. So you can calculate it. The formula is given. This is the prerequisite is digital communication. It is from digital communication. So now since we are using the unit symbol energy symbols, right? So ES is 1. Okay, so d min you can directly put it as 0.6325. Okay, no need to approximate also. Rho is average SNR, which is gamma bar here. Okay, and MR is the number of branches. Okay. So here gamma bar we have as 30 dB, that is 10 to the power 3, that is 1000. And then modulation scheme is 16 coin. So D mean we have written according to 16 coin. So error bound and probability is that it is, and for 16 coin the number of maximum number of nearest neighbor is 4, right? So nearest neighbors we will take as 4. Or maybe average number of neighbors we will have to consider. So that will also come as 4 only. So 4 times of 1000 into 0.4 divided by 4 into 5 to the power of minus 5. So after calculation, this will come as 4 times of 20 to the power of minus 5, which is 1.25 into 10 to the power of minus 6. So that is how we are calculating the upper bound and probability. So this would be answer would be B. Okay. So I think today's discussion is over. So you're just advised to go and see through the selection combining and maximal ratio combining, and just to be focused on what is asking. If it is just post processing SNR, then the formula would be different, and if it is average post processing SNR, then it would be different. So you just have to keep that in mind for the exams and other things also. So I hope this much is clear to all of you. So I'll just end the session now. So thank you and goodbye.